So we're starting at the base level, which is the hardware, the very beginning level. And we're going to create a DriveTrain subsystem, which will create or instantiate the hardware and then expose that hardware through methods so that it can be used by commands. First thing we do is we go to Subsystems and we choose New File, and we're going to create it drivetrain.java, and that'll create our class file, public class drivetrain. Public means that anyone can use it. Now, drivetrain needs to extend subsystem base. Extending means that it's going to clone that class. So drivetrain is a type of subsystem base, but obviously we're going to add to it. Subsystem base gives us a lot of functionality that we don't want to have to bother creating. So all subsystems should extend from it. It's pretty straightforward. Now within drivetrain, we're going to actually utilize two classes in our hardware. The first one is going to wrap all the motors up in what's known as a differential drive, which we're going to use because we're actually, in this case, creating a tank drive. And the other one is going to actually be the gyroscope that we're going to use. We're going to use a class from WPILib. So, private final differential drive, I can type, and differential drive. One thing to note, I'm going to bring up on this line, just in case you aren't aware, the point of every single piece in here. First, private means that no one else can access it, only inside the class. This is a matter of what's called encapsulation. It builds a sort of a wall around our class so that people don't go in and mess with our stuff. We don't want anyone touching the differential drive, and so we declare it private, which means only this class will be able to access it. Final means that once we create it, it's done. It's not going to be modified once we instantiate it. It's primarily at this point used for memory optimization, but basically final means that once it is instantiated, that's the end of the story. You cannot change it after that. It's going to be what's called a differential drive class, and we'll look at that in a bit. And I'm giving it the name of m_differential drive. That is the variable name that I'm going to use. M_ is just a convention that lets us know that it is what's known as a class level variable, because all variables exist within a scope. The scope can be within like a for loop, or it can be within a method, or it can be within a class, for example. In this case, we're going to use it within the class as we expose it. And so that's why we have it as a class level variable, because we're going to instantiate it in one method and then use it in another. So we have to make it class level. As we go forward, you'll see what that means. I'm going to create another thing. I'm going to create an ARS. This is going to be the drive Gyro. That's what they call it in WPILib. So if I hover over this and I do control period, see that? It'll tell me what my options are. And in this case, one of the things I can do to fix it, it thinks, is import com.quilabs.navx.frc.ahrs. And I'll do that, and you'll see that right up here at the top, it has added that. Now, everything is fine. So let's do this. Private drivetrain. This is the instantiation method for the drivetrain. And what I need to do now, as it tells me when I hover over that, is I have to initialize both the drive gyro and the differential drive. So I'm going to do the drive gyro first because it's easiest. And you can kind of see how it works. I'm going to call the instantiation method on AHRS, and there's a couple of them, but there you go. That's what we got. And now the drivetrain says, okay, you got the drive gyro taken care of, but now you need to take care of the differential drive. Well, let's tackle that. The differential drive is a way to put motors together and call upon methods like tank drive. So in order for this to happen, I need to have motors on the left and motors on the right. And the numbers can vary. That's part of the beauty of the differential drive. All it really cares is that there's a left side of motors and a right side of motors. In this case, we're actually going to create two left-sided motors and two right-sided motors. All right, so the first thing I'm going to do is I'm going to create a final spark. A spark is a kind of motor, and it's going to be left front drive motor equals new spark. I get the red squiggly line, I hover over it, I do control period, and it says import Spark, which is what I want to do, and that's taken care of. Now the key about the instantiation method of a Spark, the method that's used to create it, is that it needs an integer. Whatever ID on the hardware is assigned, because each motor has its own distinct ID. In this case, left front drive motor is going to be 1, and I could put it in there. But that's really not good practice because you're hard coding a variable, something that could change. Better than to do that, what you're going to want to do is put that into what's known as the constants file. Constants files are used for shared data about the robot. So I'm going to actually, within the public final class constants, I'm actually going to create what's called an inner class. It's going to be public because I need to access it from DriveTrain, for example. I'm going to call it a public final static class drive info. And each of those I'll go through and explain what they do. So public means I can access it from anywhere. Final means that once I initialize it, once I create it, it's done. There can be only one. It will not be changed. It is a rock. It is an island. Static means that I can access it without having to instantiate it. Normally when you're working with classes like cat or person or car or robot, you would need to instantiate or create that object. So it's a class until it's instantiated and then it becomes an object. So for example, you would have the class cat, but you would have the object Fluffy, right? Fluffy the cat. In this case, I don't want to have to instantiate drive info every time I want the information. This is a reference class. And so what I'm going to do is I'm going to declare it static. And that means that I can actually call upon the information within it without having to create it first. So I'm going to go in here and I'm going to create within the public final static class drive info, public final static int left front drive motor ID equals 1. Public, because everyone can read it. Final static means that it's going to be a constant. It's going to be a rock. It cannot change. Constants, by convention, are capitalized with underscores between the words. This is just convention. The computer doesn't care. A lot of the way you're going to write code is going to be for other humans. So in this case, it's going to be an int or an integer, a whole number, and it's going to be left underscore front underscore drive underscore motor underscore ID. I am not afraid of long variable names. I love them. If I can look at it and know what it is without having to dig through the code, I'm much happier. So never be afraid of long variable names. So I have this left front drive motor here. I'm going to save it by doing Control S or File Save. And when I go back over to the DriveTrain, I want to replace this one with that information. Let me close this up so we can go forward. So what I'm going to do is I'm going to call constants dot drive info dot left front drive motor ID. Notice that it automatically imported constants right here. Just threw it right in there because it knew I needed it. This is a much better way to go. What I've basically done is I've taken the coding of the variable out of this file and put it in a central repository to keep track of. It makes it much easier when you're working on complex programs with a lot of moving parts, with a lot of different people, to have a central repository of where everything is. Final Spark left rear drive motor. Whoops, let me get that. Equals new Spark constants dot drive info dot left rear drive motor ID. Now I've named it here. And again, we got the red squiggly lines, control period. I can create the constant. See, everybody knows it's a constant. It's pretty clever in drive info. Now, that constant number is going to be wrong because it has to guess what it is. We're going to go back and correct that later. But for now, I'm going to create the other two motors I need. The right front drive motor. And notice that the naming is with the first letter small and then capital of every other word afterwards. That's called camel case. right front drive motor equals new, and that's common for variables. New spark. Again, the computer doesn't care. You're writing for humans. Right front drive motor ID. And notice I just want to emphasize that I'm using long variable names. I'm not saying right front drive motor, because that's insufficient to tell me what this is. Pretend that you're writing this code for somebody else, and when they come there, they're going to want to know what it is. You aren't writing it for yourself. You're writing it for the next person that comes along, which could be you many months down the road, trying to let them know what exactly everything is. Spark, constants, dot drive info, dot right rear, drive motor ID, control period, create the constants. I'll save this by Control S. I go over to the constants file, and you'll see that it has created them just exactly where I want. The problem is they're all set to 0, because the default for an integer, which is a primitive type, is 0. It's going to go there regardless. So you actually have to go in, like I'm doing right now, and set them to the right numbers, which is what your build team should be able to tell you. All right, so I've got these great things in here. I've got that set up. Everything's happy. I'm crying. It's so beautiful. And what I'm going to do now is going to create a thing called a speed controller group. And a speed controller group is simply a collection of speed controllers. Motors, as we call them here with the sparks, are actually speed controllers. All they do is they control the speed of the motor. That's really their function. We're not actually writing to the motor itself. We're writing to the thing that controls the motor. So we're going to create the speed controller group called left drive motors, and we have to instantiate it, and so therefore we call the new method on speed controller group. And we have to pass in a list of speed controllers. Now, if you watch the video on var, where I mentioned var args, this is a var arg. I can put in as many speed controllers as I want. In this case, there's really only 2 I want. That's the left front drive motor and the left rear drive motor. And now I've created my speed controller group for the left drive motors. We have one speed controller group. Time for the other. Oops, motores. And you'll be able to tab as you get through this. You'll notice that I'm just tabbing here. That can make things really quick, as long as you don't make any mistakes. I've got my left drive motors and my right drive motors, and now I can actually create the M differential drive that I want to create. And I pass in the left drive motors. And notice it's prompting me. It's telling me what it says they are, and I'm just passing in the variables that I want. I have now created the differential drive. Now we have it, and you'll notice that this is changed from a red under M differential drive to yellow. The DriveTrain is happy. And if I actually go over here after I save this, and I go into the Gradle, and I right click, and I say build robot code, it'll run through and it will be happy. There are no errors at this point in the system. I've got it all wrong. Now, these are what are known as compile time checks. It isn't telling me the code's going to run the way I want it to. And we're going to talk about that in a bit when it comes to the right and left motors. But this is to point out that it will solve any problems that it can figure out in the code before you get there. A runtime error would be something like, let's say we left the drive motor IDs all at 0, right? According to the code, that's fine. It's just according to real life that we run into problems. One of them here is that the left drive motors and the right drive motors are on opposite sides of the robot facing opposite directions. And I have a video that talks about that, how that has to be changed. But basically, one of them actually has to be what's known as reversed. They have to be inverted so that it'll actually go, when you go forward and you give them both a positive number, it'll go forward instead of simply spinning. So once we've instantiated the left drive motors and the right drive motors, now we can actually invert them. So left drive motors dot set inverted. That's what I'm looking for. The nice thing about this is I don't have to do both the left front drive motor and the left rear drive motor. If I change the speed controller group, it'll do it for all of them. So what would I put in here? Well, I'm not going to hard code it, right? That's not a good idea. So constants.drive info. And when you're writing Booleans, which are true, false, you want a verb in there to explain what it is. So I'm going to say left drive motors are inverted. When you read that, you know exactly what I want to ask. What am I asking? Are the left drive motors inverted? Control period. I'm going to create the constant. I'm going to go fix that again later. Right drive motors dot set inverted constants dot drive info dot right drive motors are inverted, because I don't know which one it is. Oftentimes it's the right one, but maybe it's not. Maybe it's the right shouldn't and the left should. So I've updated that in constants. I'm saving this. I'm going over to my constants file. And in this case, I'm actually going to say that the right drive motors should be inverted. So I'm going to change this to true. I'm going to save this with a Control S. So these are my constants that I'm using. It's all in this one location. So now at this point, I have created both the drive gyro and the differential drive, but they're both private, which means no one can access them. This is, in effect, a brick. If you run this code, it's not going to do anything. It's going to create the differential drive, and it's not going to know what to do with it. So I have to expose methods. I have to open doors in this class to let people in to do things. But I'm not going to give them access to the motors. I'm going to have control over that. They can tell me what they want me to do with it. Just like if you went in and you said, I would like a steak medium rare, then the person who's making the steak is going to make it the way they want to. They're not going to have you in their kitchen, but you tell them what you want. So in this case, I'm going to create a method, public void drive as tank. And I need to pass in a couple things when I'm going to drive it as tank. I have to know what the left speed is. I have to know what the right speed is. And I have to know if I'm going to what's called square the inputs. And what that is useful is in the lower speeds, you have more control. I'm not going to go into that too much here, but I'm going to create this possibility so somebody could, when they instantiate the DriveTrain, call the method drive as tank and actually move the robot. So I'm going to create double, and this one's going to be left side power. I'm going to, sorry, not power. I'm going to create a double right side power, and I'm actually going to create the Boolean. Boolean is true, false. Doubles, I should have mentioned a while ago, are actually decimals. They're decimals. So when you see double, think decimals. That's really what it is. The Boolean is grant more control at slower speeds, because that's really what they want to know. They don't really want to know how it does that. I've created that. I've created this method. It's still not moving, because what I actually have to do now is I have to call the M differential drive, and I have to call its method, which is called tank drive. I'm going to pass in the left side power. I'm going to pass in the right side power. And then I'm also going to pass in that Boolean. People can determine whether they want to have it go at lower speeds or not. It's up to them. Now this is good, but really I also want to give the ability to call drive as tank without having to constantly pass in whether you want to grant more control at lower speeds. Theoretically, you decide that once. You don't have to constantly putting it in. So what we're going to do is we're going to use the constants file to actually set a setting. You can override it by passing in that Boolean. But if you don't, it's going to default to something we've specified in the constants file. So we're going to call drive as tank, and all we're going to pass in are the left side power and the right side power. Now when you do overloads like this, the solution is not to cut and paste from above. It's actually to call the method that's above. So I'm actually going to call drive as tank, and I'm going to pass in the left side power and the right side power, but I'm also going to pass in something from constants. Now get ready for this. It's going to be a long one. Constants.drive info dot square power. So for more control at Sorry, having some typing problems. Speed. What the heck? I created a really long constants variable because, to be honest, I don't mind. I really don't mind. I want to know what this constants is for. And if I look there, I can tell that I squared the power for more control at slower speeds. Now I can explain what that means at some point. It has to do with how it's graphed. But what this basically means is that at the slower speeds, when you're moving the joystick forward, it is less responsive. And the more you push it, the more responsive it becomes. That enables you to have a lot finer control at slower speeds. So we have this drive as tank exposed. If somebody instantiates the DriveTrain, now they have two methods to call. And obviously we also, we could simply set the speed to 0, but why not simply have a method called stop driving? And that one is simply differential drive dot stop motors. All right. So we've created 3 methods after instantiating the hardware. And those 3 methods will be used by all the commands to run this beast. We can add more as we go forward, but for right now, this is all we're going to have. I also want to show you how you do with a gyro, because the gyro is unavailable at this point. So we're going to put in public void reset drive gyro. And in here, I'm going to call the method that's on the drive gyro called reset. Now you'll notice that I'm actually calling methods on the classes the objects that I've created rather than exposing the objects. This is good coding. It means that they cannot go in and mess with that object in ways I don't want them to. They can only tell me what they want, and then I go and do it. So this is pretty much done at this point. We've created the DriveTrain. One final thing I want to show you about subsystems. One of the great things about subsystems, and we'll talk about this when we get to the command scheduler, is they have a method inherited called periodic. You can override periodic, which means you're going to take control of this method and tell it what you want it to do. If you don't, it'll use the periodic method that is defined by the ancestor. That's what super periodic, by the way, does as well. The super is actually your ancestor. So it's simply saying, run the periodic that my ancestor did. But let's say that in here with the gyroscope, I need to every 20 milliseconds update what we're doing on the gyroscope, where our X and Y and Z are. So let's say I have I'm going to create a method called update gyro info. All right. And whenever this periodic method is called, it will run that update gyro info. And then I can expose that information to whatever needs it. For example, whatever is using this subsystem, whatever drive system is using the subsystem, will find out information from the gyroscope that it needs. So this is what this periodic method is used for. It's only used for updating hardware information, not for making outside commands. Remember, separation of concern. The focus of the subsystem is the hardware. That's what it cares about. What we're going to look at next is how you would actually utilize that in commands. Because now that we've created the hardware and we've made it available to commands, we actually have to create the commands that will use it. So that's what we'll tackle next time. We'll see you when we tackle commands.